Welcome everybody to the very last presentation, because we should be docking tomorrow, right? Yes! Unless something else happens. Who knows? Yesterday I asked you to join with me in thanking the guys at the back there, Dean and Gabor, for the excellent job they've done with the difficulties they've encountered. I did forget to mention where they came from. Dean's from South Africa and Gabor's from Hungary. Hungary is perhaps not the best country to be from when you're on a ship like this with all the food available. That's a pun. Okay, it didn't work any better the second time I told it. So today we're going to talk about radiation. What is radiation? So when you hear that, what goes through your mind? What do you think of? And that's kind of a rhetorical question. If I was in a different format, I'd come around and I'd talk to you and say, what do you think? And the first thing that some people will think of is this, which is the atomic bomb, the dirty bomb, an explosion, radiation, nasty stuff, fearful stuff, Fukushima, Chernobyl, etc., etc. But it's other things as well. You'll probably recognize this picture. Anybody? Chernobyl, yes. There were a couple of suited individuals looking at Chernobyl. They're wearing self-contained breathing suits to prevent internal contamination. This does not protect you from radiation per se, because those suits aren't made of 10 feet of lead. Gamma radiation will go through those. Here's one you may not think of, Spider-Man. Do you remember how Spider-Man got his powers? He was bitten by a radioactive spider. You remember that? Yes, radioactive spider. Here's another one. I spoke about this in one of the other talks, where you get to put your feet in the aperture there, look through the top and see how well your shoes fit. And I actually remember doing that. Maybe some of you do too. Yeah, I see a few people nodding that they did it as well. Of course, you don't find them there anymore because they were giving off X-ray radiation. Did you think of this one when I said radiation? Yes, you see a nod there, a hand there. This is our sun, this is our star. It's a giant fusion reactor, and part of the things that are produced in there are radioactive, and there is all kinds of radiation coming out of the sun. And thank goodness it does. Because as you see when we get into this, that radiation is essential for us to live. Without it, we would not be here. Do you think of this when I talk about radiation? Bananas, watermelon, Brazil nuts, and even potassium chloride water softener crystals. If you ever go into a Home Depot or a big hardware store that has the potassium chloride with a radiation meter, you can actually measure an elevated background standing next to that pile of bags. And I have actually done it. It's a very small elevation, so don't worry. Bananas, potassium, watermelon, potassium, Brazil nuts, radium. They have elevated radium in Brazil nuts. Again, not harmful to you, so don't stop eating them. The way my wife has been devouring watermelon up in the buffet, she should be glowing by now if there's a problem.
And I am.
Well, she does glow, but it's a different kind of glow. She is quite luminous in her own right. Now, the radiation that the whole spectrum encompasses is really divided into two sections. There is the non-ionizing section, and there is the ionizing section. The non-ionizing section contains things like radio waves, microwaves, infrared, which is heat, and into the UV band. And the UV band is where you switch from one side to the other, because the ionizing section contains the X-rays. I've included alpha and beta radiation there too. They're not really electromagnetic, but they do come under radiation, gamma rays, and ultraviolet. Explains everything. It really does. And we can read pretty much most of it, actually. On the side screens, it's a little better focus, so you might be able to see it better there, but let me walk you through it. Ultraviolet's divided into three bands. You've heard of UVA and you've heard of UVB, I hope, because you've all been reading your sunscreens and you'll know that your sunscreen is good for protecting you from UVA and UVB. There is another one called UVC. UVC is much more energetic. It occurs at a lower wavelength and it is ionizing completely. Fortunately, as this picture shows, the atmosphere is cutting out all of the UVC. It's also removing quite a bit of the UVB, but some UVB is getting down to the surface of the Earth, and the UVA is getting right through the ozone layer. These radiations that ionize can damage the DNA that you see circling over there, cause breaking, a single strand break, often repaired by the enzymes that we have developed through our evolution. It turns out to be a double strand break, which is less likely with this kind of radiation. That repair can be more difficult, and indeed it can lead to cell death or mutation. But so can the single strand break. It can also lead to a cell death or a cell mutation, although less likely. In one of the talks previous to this, I mentioned that there was a big radiative explosion far off in space. The gamma rays actually reached our Earth, caused a few minor problems. They were measured. The supernova was SN 1987. Had that supernova been closer, that radiation burst from it would have obliterated the ozone layer, and the UVC would have wreaked havoc on the surface of the Earth, possibly destroying the food chain and all the associated problems with us. So you probably... Natural radioactivity. There's other sources of radioactive material around. It's not just all man-made. Some of them have been with us since the dawn of time. There's 35 of them. Uranium and thorium are well known. Potassium is another one. There are others that are created in the upper atmosphere by the cosmic ray bombarding. The atmosphere, carbon-14 and tritium are produced up there. And indeed, that's the carbon-14 that we use in a dating process. That's where it's being made. And then there are others, 51 of them, that are products of either decay chains or another source. But they're all with us. Then, of course, there's atomic reactions. You're familiar with nuclear reactors. So what do you have in you as you sit there thinking, oh, I don't have a problem? Well, you do. That's what you've got inside you now, typically. So potassium-40 we all have. Potassium-40 is a naturally occurring radioactive material. It is part of potassium. You can't separate it. It's a fraction of a percent of potassium. Carbon-14, I said, it's produced in the upper atmosphere, and most of our body is made out of carbon. Well, not most of it's water, but the carbon in our bodies also has a component that's radioactive carbon-14. Rubidium-87 is an odd one, but it's everywhere. It's very hard to get rid of that. It's similar in its chemistry to sodium, salt, so it's very soluble. Lead-210 is part of the decay series. You can't get away from that. Tritium, another one made up in the atmosphere. Uranium, I regret to tell you, is ubiquitous. It's in almost everything. Often in glassware, for example, it will leach out. It's in most of the foods we consume, but it's very low. You have radium-2, radium-228 and radium-226, also part of the decay series, the natural decay series. But let's focus on potassium-40 because obviously that's the one that's highest. So the figure that you saw on the previous slide was a little over 4,000 becquerels. Well, what's a becquerel? It's a disintegration per second. So let's run through the calculations and see what we've got. How many disintegrations per minute? Well, multiplied by 60, it's 260,000 odd disintegrations per minute in your body as you sit there for nominally a 70 kilo person. Translate that to per hour. Well, it's 15 million. How many per day? It's 374 million. And how many per year? Then we go up into the high figures there. That's a trillion, isn't it? Well, almost. 137 billion. 137 billion annually. Disintegrations in your body. Radioactive decay. Are you all feeling safe? Because this doesn't hurt you, does it? Because you're here, aren't you? And everybody else is, for that matter. But we've all got it. And don't try and eliminate potassium from your diet, because it's essential for the workings of your muscles. So you can't get away from it. So when you cuddle up tonight to whoever you're with, you're getting an extra dose from your partner. So I'd like to let you know. Then there's the low dose effects, which what most people are concerned with. There's a lot of fear here. There's actually 3 effects that come out of low dose effects. The first one you're all familiar with, which is cancer. Not so long ago, they discovered that cardiovascular disease can also be caused by low doses of radiation. But the good news here is that it's got a threshold, and then there are DNA mutations. Let me show you this picture. My wife's just told me I've been talking too much. That's a passionate subject. This is the cancer risk here. There are 4 models really, that we think about. We've got a lot of high dose data over on the right, and then the way one estimates what's going on at low dose is you use the high dose data and then you extrapolate backwards. And the further you extrapolate backwards, the more uncertain your model becomes. So the easy one is linear. That's the linear no threshold theory, which causes us no end of problems in the industry because you get down to ridiculously low doses that you have to regulate against, and they really don't cause end of this presentation. I think we have time for a few questions, do we?
Yeah, we do. 10 minutes.
We have 10 minutes, so if there are any questions, please raise your hand.
Try to get out of here.
The runner will be on her way. There's a question on your row in the middle, there's a question in front, and then there's another one down here, and there's one way at the back. So, I've seen you all, and we'll try and get to you.
I always hear about radium and radiating in the basement. Is that of any concern?
Radon.
Radon.
Yes, radon. Is radon a concern? Yes, absolutely it's a concern. It is being attributed to be the second leading cause of lung cancer. So it is going to depend on the level of radon in your house. Nominally, the limit, the safe limit, has been set at 200 becquerels per cubic meter, at least in my country. You have different units in the USA, if that's where you're from. Where are you from? Oh, well, it's 200 becquerels per cubic meter. If you measure it and you have higher values than that, it's relatively simple to remediate. You can do it yourself for about $2,000, or you can hire someone to do it for more. The only problem with getting a radon measurement done in your house is if you use what's called a grab sample, which is somebody comes in with a monitor, sucks some air through it, goes away and then gives you a result. That is a very unreliable measurement, unfortunately, because radon is both diurnal and seasonal. So you'll get more of it at one time of the year and you'll get more of it at one time of the day. So it fluctuates. It fluctuates daily, it fluctuates seasonally. So to get an accurate picture of what you've got in your house, you've actually got to do a test that runs for about 6 months if you want to do it properly. Okay? Right, back there. And then, Ludi, you need to come down to the front as well.
I just wondered, because with the radiation couple of years Japan have experienced, when we travel to Japan, should we worry about the food, the water, and all the products they grow afterwards that we consume when we visit in Japan nowadays?
Are you going to the reactor site?
I don't know. We're going to Kyoto and Tokyo.
Well, the simple answer is no. The Japanese have done a pretty good job. There are areas around Fukushima that have been contaminated. There are limits on some of the food products from those areas, but on the whole, the Japanese government have done a reasonable job in containing it. Now, I did say this in one of the earlier presentations. The number of dead from the Fukushima earthquake tidal wave was, my recollection, about 3,000. the number of dead from the radioactive releases from Fukushima is currently standing at 0.